Hey everybody, this is a video summary of the ideal gas law. The ideal gas law is used to calculate volumes and pressures and temperatures, etc., um, involved in gases, which for the most part closely follow the ideal gas law. We will learn later on in the semester that actually there are certain conditions, such as high pressure and low temperature, where certain gases deviate quite a bit from the calculation we're going to do. But for now, we're just assuming that all gases are going to follow this equation known as the ideal gas law, which is pressure times volume equals the number of moles times a constant called the gas law constant times temperature. So this is sometimes known as Pivnert, as you know, because you just run the letters together. It's chemists aren't that creative about these things. Anyway, so the P here is the pressure. The V is the volume. N is the number, get it? N number of moles. R is the gas law constant. We're going to have to deal with that, but I'm going to come back to that in just a second. The gas law constant, and then T is the temperature. The temperature here has to be in Kelvin, so it's very important that you remember to change your temperature to Kelvin, which if you recall, the temperature in Kelvin, that's not right one of that. The temperature in Kelvin is just the temperature in Celsius plus 273, okay? So we're not going to use Celsius anymore, really, except for like a week, second semester when we do some calorimetry stuff. We're pretty much going to focus entirely on Kelvin. All right, so this gas law constant, this R value, becomes a bit of a problem. There's actually like a million different values for this, depending on what units you use. For right now, we're going to use two possible values. So R can be either 0.0821, and then it has this really goofy unit system, atmosphere liters per mole Kelvin. Why are the units so goofy? Because it's the gas law constant is here in the equation basically to make all the other units cancel out. Okay. Now what that's going to mean is that if you're using this value of R, your pressure over here is going to have to be an atmosphere. However, there's another value for this that we're also going to use sometimes, which is 62.36 torr liters per mole Kelvin. And torr is a unit that we haven't used a whole lot, but it is it's a unit of pressure. So if your pressure over here is given in torr, you're going to use this value of R. And if your pressure is given in atmospheres, you're going to use the one on the left. Okay. It does mean that, notice that in both of these, the volume is in liters. So it does mean your volume is always going to have to be in liters in your equation. So sometimes, and I tend to do this a lot because we tend to measure in milliliters in the lab. So pretty frequently, you're going to have to remember to change that to liters. Just remember that there's 1,000 milliliters in 1 liter, which means to go from mils to liters, you just divide by 1,000. Okay, so that's kind of the quick overview, probably none of which makes any sense until you actually apply it. So let's work a practice problem. So what is the pressure of a sample of 12 grams of nitrogen at 25 Celsius with a volume of 100 milliliters? All right, so we're going to first off use the ideal gas law, PV equals nRT, and it helps a lot to just go through the problem and see what we have. So we have temperature, right? Except it's in Celsius, so remember we're going to add 273 to that. So our temperature is going to be 25 plus 273, which when you plug that in the calculator is 298 Kelvin, right? Notice that we're given the volume, but we're given it in milliliters. So our volume, we're going to divide that by 1,000. So that's going to be 0.100 liters. I'm just moving the decimal place 1, 2, 3 times to the left. Okay, if you prefer to get your calculator out and divide that by 1,000, you're welcome to. It just costs you a little time. So as you get more comfortable with this, going from mils to liters is just 1, 2, 3 times over. There's where the decimal place is going to be. All right, so we're looking for pressure because it asks us what is the pressure. So I'm going to write P equals question mark. Oh, and it didn't ask us for units. Let's go ahead and stick a unit here. So what is the pressure in atmospheres? So let's say that we're asked for this in atmospheres. So the value of R we're going to use is the 0.0821 atmosphere liters per mole Kelvin to match the units that we're asked for, which is atmospheres. Now, the thing we don't have is N, but we have a way to get to N, okay? So we're given that there are 12 grams of nitrogen, and we can take nitrogen, because we know how to, we've been doing this for like weeks now, right? So we can just change grams to moles, get out our calculator. 12 divided by 14 is 0.857 moles, all right? So that's going to be our N value now, all right? And this is pretty typical that you're going to have to do some calculation or other to get to the number of moles, or sometimes you get the number of moles and convert it at the end. But so you just have to be a little bit flexible on that, and remember that you already know how to do that. Okay, so now we can finally deal with this equation, right? Because we have all the things we're going to do. You have two choices with the equation over here. You can solve and then plug in, or you can plug in and then solve. I don't really care which one you do because you get the same answer either way. I find it much more convenient to solve and then plug in. So I'm going to isolate pressure here by dividing both sides by volume. So that cancels out. So now I have pressure equals nRT over V. And now I've got my collection of variables over here, and I'm just going to plug them in, right? So I know the number of moles is 0.08257 moles. And yes, I'm going to be really picky that you plug in the units here. It drives me nuts when people don't do this. So I will count off if you don't use the units. 0.0821 atmosphere liters per mole Kelvin. The temperature is 298, and I know I'm running into this. I'm going to move this over. Oh, good. Not even slightly right. Okay, that didn't work. We can do it this way. Yeah. If y'all have never noticed, I have a real big, I like to do this in one take because I have to make a lot of these, and it doesn't do me a lot of good to make them perfect because they're never perfect. So 298 Kelvin, that's a 12 back up there. Okay, and the volume is 0.1000 liters. All right, so we finally get to crunch this guy through. 21 times 298 divided by 0.1. So that comes out to be a pressure of, oh, this is annoying. So it's 210, but I need 3 significant digits, so like that. Okay, so this is going to, now you'll notice here that liters cancel with liters, kelvins with kelvin, mole with moles. The unit you're left with is atmospheres, which is what we were asked for. Okay, so that means our pressure here comes out to be 210 atmospheres, which is quite high. But you have a lot of nitrogen in a very small volume, so that kind of works out. This is like surface of Venus type pressures that, that can happen. It's not something we encounter a lot on Earth, but or in our normal everyday life. Okay, all right. So that's the first thing, is just working out all the unit business, changing your temperature to Kelvin, getting your volume in liters, picking the correct value of R to use. All right, and then if you're given grams of something, changing that to moles. All right, and then plug everything in. All right, so beyond that, it's pretty much just an equation. You guys are pretty good at handling equations for the most part, and you know not to be intimidated by it. Okay, all right. So now here's where it gets tricky: is that we're chemists, right? So of course we're going to bring chemical reactions into this, right? And this is really why I like to teach this as part of the stoichiometry unit, because it's really like the last piece of material you need to really be able to do all sorts of stoichiometric conversions. So here we're given a practice problem where we're told 37 grams of hydrogen peroxide. This is the stuff that people use to treat cuts, or sometimes people use it for ear infections and stuff. If you have 37 grams of hydrogen peroxide and it decomposes, what volume of O2 is created at 35 Celsius and 770 torr? Here's that weird pressure unit that we're not used to, torr. And then we're given a chemical reaction. So let's organize our information. So we've got 37 grams of hydrogen peroxide. and we're interested in the O2. So we're interested in what volume. So I'm going to put a volume question mark. We're given the temperature is 35, but let's just add 273 to that right now. Okay. And so that's going to be 308 Kelvin. And we're given that the pressure is 770 torr. All right. Just by the way, a torr is the same as a millimeter of mercury, which some of you may have heard of, depending on other classes you've taken. They're the same thing, but torr is the, I don't know, more correct version of that or something. It tends to have become more predominant in the last 30 years. We always used millimeters of mercury when I was your age. Anyway, you don't care. So now, but we're going to have, so notice here that for PV equals nRT, right? PV equals nRT. You always know R. We're going to use the torr value of R. You're given the temperature, you're given the pressure, we're looking for the volume, but notice we don't have an N to plug in. Well, how do we get the N? Well, that comes from the 37 grams of hydrogen peroxide that's decomposing, because you all are really good at stoichiometry now, especially gram stoichiometry, so you all know that we can change this from grams to moles. So that's going to be 2 times hydrogen plus 2 times oxygen. I should probably know this one off the top of my head. This is 34.02 grams of hydrogen peroxide per 1 mole of hydrogen peroxide. All right. And now, but notice, so that's moles. And sometimes people get here and they're like, oh, look, I have moles. But you don't have moles of the gas. You need moles of the O2. That's what you need, is moles of O2, not moles of hydrogen peroxide. So we got one more step here, which is we're going to say for every 2 moles of hydrogen peroxide, of the H2O2, there's 1 mole of O2 that gets generated. So now we're going to calculate that, 37 divided by, in parentheses, 34.02 times 2, and that comes out to be 0.544 moles of O2, all right? So that's what that's the value we're actually going to plug in here. So now we finally have an N, 0.544 moles of O2. By the way, when you plug this guy into your calculator, remember to do 37 divided by, in parentheses, 3402 times 2. If you don't get that 2 in the parentheses in the denominator, you'll get something like 2 something, and that's wrong. Okay, make sure you get that 2 in a parenthesis in the denominator. Cool. All right, so now we can finally solve for this guy. So we've got PV equals nRT, and I'm going to do my thing and solve for V. So V equals nRT over P. And now I just plug in, because we've done all the hard work. Now we just have the equation part. 0.544 moles. We're going to choose the torr value for the gas law constant R, so that's 62.36 torr liters per mole Kelvin. And I know that unit sounds goofy, but you'll get used to it. Times 308 Kelvin, all of which is over pressure. Where'd my pressure go? 770 torr. Okay, torr cancel, Kelvin cancels, mole cancels. We're left in liters, so we're going to get a volume here in liters. So now we finally get to punch this through our calculator. 0.36 times 308 divided by 770. That gives us a volume of, let's see, 3 significant digits, so 13.6, and that's going to be in liters. All right? Okay, so let's step through it again. I organized my information under the reaction equation, figured out what we had, what we were missing. We were missing the N value, so we did a stoichiometric calculation to find that N value, starting from the mass of the hydrogen peroxide over here. And then came back, once we had that number, now we get to plug that into PivNert, crunch the data, double check that our unit, what unit we're getting, and that's our answer. Okay, all right. I know it's a lot. I know this can seem a little overwhelming at first, but it's really not that bad. once you have done a few practice problems on it and built some confidence up on it, and just you learn to always pick the right value of R and that sort of thing. Okay? All right. So now I wanted you to do a practice problem. So go ahead and work this problem. Pause the video, get out a piece of paper and a periodic table, work the problem, and then once you're done working the problem, hit play and watch me do the solution. All right, I hope you've had a chance to work the problem. So we're asked how many grams of sodium carbonate are required to generate 500 milliliters. This is all the CO2, 500 mils of CO2. Oh, and you know what? I made a significant digits error here. I really hate it when I do this. So there should be a decimal place there. There's no way that you would only have, anyway. I'm going to work this with three significant digits. If you did it correctly the way I wrote it with one, awesome blossom. So, all right. But it's going to really screw it up to work it with one. And we've got, so let's go ahead and change that volume 1, 2, 3 to 0.5 liters. And actually, I'm going to move all of this over a little bit because I've got no space to work. So I've got 0.500 liters for my volume. I've got a temperature of 25, but if I add 273 to that, that comes out to be 298. So it's 298 Kelvin. You'll memorize this one after a while because we use 25 a lot because that's like a normal room temperature. And then we've got a pressure of 0.95 atmospheres. Right. Incidentally, if you're not used to the pressure units here, 1 atmosphere is like normal pressure, air pressure at sea level on like a sunny day. And 760 torr is the normal air pressure at sea level on a sunny day. So just to give you some reference there. Anyway, we don't have an N value, so what we're trying to get over here to the sodium carbonate. So this is the reverse of the problem we just did a minute ago, right? So in the problem we did a minute ago, oops, too far, we were given the amount and we had to calculate our N value, right? But now what we're going to do is we're going to calculate an N value now. We're going to use that to get back over here to the grams of sodium carbonate, okay? So this requires just a little, my philosophy is always if you can do the problem forward and backwards, you actually get it, okay? So this is one of those cases where you actually had to work the problem backwards from the example I gave you, all right? And if you got stuck, totally understandable. Just, that's why we're going through it, right? If you already knew it, you wouldn't be watching the video. Okay, so we're going to now take Pivnert, and we're going to solve for N. So I'm going to divide both sides by RT to isolate N. So N is now P times V over RT, which our pressure is 0.95 atmospheres. Our volume is 0.500 liters. We're using atmospheres here, so we got to pick the 0821 R value, atmosphere liters per mole Kelvin. And the temperature is 298 K. Kelvin cancels, liters cancel, atmospheres cancel. We're going to end up with 1 over moles, which turns into moles. So that, now we get out our calculator and punch everything in, 0.95 times 0.5 over 0.0, oops, I almost did the thing I was warning you all about. I forgot to put my parentheses in the denominator. Open parentheses, 0.0821 times 298, close parentheses. That comes out to be 0.01, and actually I've got 2 significant digits here from the atmospheres. So 0.019 moles. Now, what is that moles of? That's moles of CO2, right? Because this thing over here is the ideal, say it with me, ideal gas law. So that always gives you moles of the gas. But I asked you for grams of another substance over here. So now we got to do a little stoichiometry. Okay. So there are 2 moles of CO2 for every 1 mole of sodium carbonate. And 1 mole of sodium carbonate is 22.99 times 2 plus 12.01 plus 3 times 16 105.99 grams of sodium carbonate. And once again, this is one of those cases again where you got to label your substance. If you just write down moles, you don't know what it's moles of, and you're going to make mistakes. So moles of CO2 cancel, moles of sodium carbonate cancel. You've got grams of sodium carbonate. That's what you were asked for way back over here at the beginning of the problem. So looks like we're in good shape. Punch that in the calculator, and I come up with 1.0 grams of sodium carbonate. Okay. So if you were doing this with excess hydrochloric acid, you would weigh out 1.0 grams of sodium carbonate. You'd react it. You'd generate 500 mils of CO2, as long as you're doing this at 25 degrees, and 0.95 atmospheres. All right. So again, this was a little different than that previous one, right? Because we had to figure out, oh, I don't know N, but I can solve for it. And that will give me the number of moles of the gas. And then I just have to do some stoichiometry to get from moles of the gas over to grams of the sodium carbonate. All right. Okay, folks, I hope this was helpful. I know it was a little long, but there's a lot of details in this one to go over. So please